Okay, so just to review, we talked about end behavior when referring to polynomials, and it means the same thing in this context with a rational function. End behavior refers to what does a function's y values do when x gets very large, either in a positive or a negative fashion. So we're looking at, on the x-axis, what's happening way over to the right or way over to the left. New York and Los Angeles, if you will. That's what we're going to investigate today. So to kick off this discussion about end behavior, we're going to look at three different rational functions, which I have labeled here in columns B, C, and D as R, P, and Q of x. You have x cubed minus 1 over x plus 2, x cubed minus 1 over x to the fourth plus 2, and x cubed minus 1 over 3x cubed plus 2. We're going to start to plug in values of x that are getting larger and larger into this function, and we want to see what kind of y values come out. And we'll do the same thing for x values that start to get big in a negative fashion. So recall that if I want to have Microsoft Excel do a calculation, I have to start with an equal sign. And since I have a fraction, I'm going to go ahead and put parentheses divided by parentheses so I don't have to do it later. I have to have the numerator surrounded by parentheses and the denominator. Okay, so for r of x, to input 100, I want to click on the 100, and so cell A2 is highlighted there, and I need to cube that number and then subtract 1. And in the denominator, I want to have that number plus 2. I press enter, and it does the calculation for me. Now Excel's smart, and we'll use relative cell references if you will double click on this little blue square. And it should stop once you get to row 6, because there's nothing below row 6. Okay, so we can see that x starts to get larger and larger and larger when, the r of x values get larger and larger and larger as x gets large. So this looks like the same thing we saw with polynomial functions. Let's do the same thing for negative 100 up to negative 1 million. So equal sign, two parentheses, with a fraction bar. This number cubed minus 1, sorry about that, just click here, divided by this number plus 2, and I want to fill down. Okay, in this case the numbers get large in a positive fashion as the x values get big in a negative fashion. Okay, so far that's one possibility that a rational function could take on when you look at its end behavior. It could do the same thing polynomials do, which are either get very big positive or very big negative. Let's take a look at P. So again, fraction, parentheses. I want to take this number, cube it, subtract 1. This time we're going to divide by this number to the fourth power plus 2. And I want to fill down. Alright, and so in this case, I get a pretty small number, 0.009, etc. And these numbers are going to get smaller and smaller, closer to 0, looks like, using the 5 numbers as evidence for that. It's a way to guess. That's what Excel does for us. It gives us estimates. It doesn't do anything officially. Alright, let's take a look on the other side. So this number, cubed, minus 1, divided by this number to the fourth plus 2, fill down. And these numbers are negative, but again, they're getting closer and closer to 0. So here's a possibility that a rational function, when you make x very large, positive or very large negative, actually gets close to a certain number, in this case 0. Let's look at one more example, q of x here, equals, parentheses, divided by parentheses, this number cubed minus 1 divided by 3 times this number cubed plus 2. Fill down. And it looks pretty convincing with these 5 numbers that this y value gets closer and closer to 0.3 repeating, which is a decimal for 1/3. Let's take a look at the other side. This number cubed minus 1 divided by 3 times this number cubed plus 2. Fill down, and we see the same numbers pop up. Okay, so let's head back to our notebook file and discuss what we've seen, and then we'll talk about the algebra that will reveal this to us without having to use the spreadsheet. Okay, so we saw three different functions in the Excel spreadsheet. These were the functions R, P, and Q, and we saw that R had y values that got very large when x started to get very large. So here's the graph of R, at least a pick part of it, and when x starts to get big, you can see that the y values start to get large. Basically, R behaves like a polynomial when x gets big, positive, or big, negative. Okay, P of x we saw, the y values leveled off towards 0 when x got large, positive or large, negative. And we can see that in the graph here. The graph starts to head down towards the x-axis on both sides. In this case, up towards the x-axis, but starts to hug the x-axis as x gets big. So a rational function could level off to 0. And then function q, we saw the y values level off towards a number besides 0, 1/3 in this case, and we can see that revealed here in the graph. So these are the three basic scenarios that can happen. You can have a rational function behave like a polynomial, which means the y values get large, either positive or negatively. You can have a rational function that has its y values level off to 0, or you could have a rational function whose y values level off to some other number. Now, before we get to the actual algebra that will show us this, let's just make a little quick definition here. Okay? If the y values of a function f start to level off to some number, let's call it k, as x approaches positive or negative infinity, so as the x values get big, the y values approach this number k, then we call the line y equals k, which recall is a horizontal line. Okay? That line is called a horizontal asymptote of your function f. So that's kind of a pre-cal definition for what a horizontal asymptote is. In calculus, we'll get a little bit better definition, make it a little bit more clear. Okay, so what is the algebra that helps us find these horizontal asymptotes, or tells us that there are no horizontal asymptotes? And the answer to that, actually, believe it or not, is long division. So we're going to use long division, and we're going to look at the quotient of the long division problem. So if you'll recall, we've been writing long division problems in the form p of x over d of x, okay, your polynomial divided by a divisor, is equal to a quotient function plus a remainder function divided by your divisor. And so when we want to determine if there's a horizontal asymptote or not for a function, we're going to be looking at this q of x. And we'll take a look at some examples to see what I'm talking about here. So these were our three functions that we looked at, r, p, and q, and we've done long division. You can check this later if you want, but I saved us the time of actually doing the long division. If we divide x cubed minus 1 divided by x plus 2, we end up with this answer down here. And we have a quotient of x squared minus 2x plus 4. A remainder of 9 divided by x plus 2. Okay, now what I want you to understand here is why this works. So I'm going to submit to you that your remainder divided by your divisor will always approach 0 as x gets big positive or x gets big negative. If you think about this remainder right here, you have a constant 9 divided by x plus 2. So if I was to plug in a very large value for x, say 1,000, okay, 9 divided by 1,002 is going to be pretty small. And the bigger you make x, the smaller and smaller this remainder divided by divisor piece becomes. So essentially, that doesn't matter when x is big. And so we focus on the quotient, the x squared minus 2x plus 4. That's the reason why r of x behaves like a polynomial. The quotient ended up being a polynomial. So r of x behaves like this polynomial. X squared minus 2x plus 4 as x approaches positive or negative infinity. And we know how polynomials behave. In this case, x would get, as x gets big, positive, the y gets big, positive, and as x gets big, negative, the y gets big, negative. Now, if you look at p of x, we can't long divide p of x because the divisor has a bigger power than the dividend. So what does that mean if I can't do the long division? Well, let's think about this for a second. We talked about how polynomials basically behave like their leading term. The leading term drives the train. So I have an x cubed and an x to the fourth as leading terms. So if I just ignore everything else and just look at the two leading terms, I have x cubed divided by x to the fourth, which would simplify to 1 over x. And as x becomes very large, 1 over x will become very small. Why is that? Well, if I plug in a big number for x, I have a number, 1, divided by a very big number. That's going to get small. And the same thing happens as x gets big in a negative fashion. So, if the power of the denominator is larger than the power of the numerator, then your function will have a horizontal asymptote of the x-axis. 0 will be the horizontal asymptote. Third scenario, we do the long division. X cubed minus 1 divided by 3x plus 2 ends up being 1/3 minus, actually ends up being 5/3 over 3x cubed plus 2, but I just rewrote that a little bit simpler. So our quotient in this case is a constant, 1/3. Remember that the remainder will always approach 0 as x gets big, positive or big, negative. So in this case, our quotient was 1/3. And so the line y equals 1/3 is a horizontal asymptote to the graph of q of x. So again, this is the skinny on this. You do long division, and your quotient, if it's a constant, is the horizontal asymptote. If your quotient is a polynomial, then you don't have a horizontal asymptote. And if you can't do the long division, then your horizontal asymptote is the x-axis, the line y equals 0. So here's the synopsis that you can take with you. So it says, upon long division, if the quotient of a rational function f is a constant k, then the line y equals k is the horizontal asymptote for the graph of f. If the quotient is a polynomial, then the rational function has similar end behavior to that function, to that polynomial, and does not have a horizontal asymptote. And finally, in the rare cases where long division is not possible, then the line y equals 0, or the x-axis, is a horizontal asymptote for the graph of f. So, you now have the ability to find horizontal asymptotes, or at least to talk about end behavior of a rational function. In our next video, we'll put what happens on the interior with the end behavior and be able to put it all together and graph rational functions pretty accurately.